which will be delivered by Rajadas. And the title is Comparison of 1D Truss and 3D Solid Elements in Developing a Simplified Finite Element Models. So of course the presenter is myself, the last presenter, and lunch is a bit way away. So I will try to be simplified and quick as well. So what I want to talk about, a bit of background, which is in the same folder, sessions. Yeah, and yeah, that one, PowerPoint is, yeah. So the background of this presentation is, we always, as engineers nowadays, for academic work, we move on to make the models more and more complex, to accommodate more physics, more accuracy, which is great. And I have been doing it for a long time. My previous work on this area was a multi-scale damage model to model fiber reinforced composites, which kind of adopted the similar approach as one of the presenters presented, using warp element, web fibers, matrix models separately, using different damage scale, using different multi-scale effect and multi-scale geometric effect. Now, I hit a barrier when I was working on this simple thing called soft body armor for low velocity impact protection. Basically protection against stab or low velocity projectile impact. So when this project came for Australia's Defence Force, so they asked me to develop an optimization scheme, which means this fabric, if you look at the complex architecture of the fabrics which is produced to produce armors, you have an endless possibilities of how you organize this architecture and the materials, what you choose for. You can use a single monolithic material, you can hybridize fibers, particularly Kevlar and glass fibers and other different types of fibers. So there are possibilities in terms of materials and in terms of fabric architecture. And what we wanted to do, develop a system which will be a response surface optimization considering numerous architectures to plot the best armor behavior or best impact protection or impact resistance of such fabric. So when I showed my multi-scale model to them, they were very scared. They said, look, we have graduate engineers in our lab. We don't have many PhDs. So they won't be able to run your three-stage model with a fully coupled. So can you not go back to your basics and come up with a simple model, which will do our job? That's the most important thing. So I kind of went back in time, looking at developing a simplified model for basically studying impact response of Kevlar fabrics, with the objective this model can be used for very rapid, fast running of finite element simulation to predict the response. As you know, we can do only limited tests, impact tests with such kind of fabrics, but if you want to do optimization, you need to run numerous such analysis to evaluate your objective functions, sensitivity, and then get the optimized design. So my co-author was Norberto Feito. He was an intern, or he was a PhD student who spent about 6 months with me at Royal Melbourne Institute of Technology, which is located at Melbourne, Australia. So we both worked together along with my colleague, Ali Daliri, who is an expert in impact structures. So very standard structure. I'll talk about the background, which I did, objective, model implementation, validation, and simulation, and conclusions. So this would be a bit of relaxed presentation, preparing you for upcoming lunch. So all we know, if you're not familiar with this very common fabric called Kevlar, which is basically the commercial name is Kevlar, but actual name is Aramic. It was very popularized and discovered by Stephanie Kolek in 60s basically, and the registered brand is DuPont Aramid fibers. They are synthetic compounds which has got great, excellent mechanical properties, particularly for armor applications, and in this case we focus on soft body armor, soft armors for low velocity protection. We didn't do the high velocity impact in this case. It has very high Young's modulus, high ultimate tensile strength, it can absorb high energy, and it can stretch a lot, so we can have elastic deformation. The properties are not very sensitive to temperatures, and it allows for, as a result, it allows for very lightweight, flexible protection gears. And it's a very popular material for developing armor, soft armor particularly, but if you infuse it with matrix such as epoxy, you can also develop hard armor for composites, made of composites. So these are the properties which are taken from literatures, but notedly, we have a woven fabric. So we have a warp yarn and fill yarn, which is on the other direction, and they have different properties which we measured basically from the laboratory. In our lab, we measured these properties, and we'll be using this in our model as input parameter. So when we talk about the simplified model, what is the simplification and why we did it? So and if we know any mathematical model or numerical model is nothing, but the definition is abstraction based on a set of rules that allows us to make predictions of a system behavior. So we went to this copybook statement to develop our simplified model. Can the model do accurately what we need it to do? So when you model such a woven fabric, you have different level of complexity, such as a membrane model, 1D yarns, 2D yarns, or you can use 3D solid elements for the yarns as well, which is going in the more complicated model. And we can use multi-scale, multi-level model. So multi-scale geometry, and if you have failure, you can have multi-scale failure model, which we did in the past. So if we have simplified models, thing is that a model must have control over variables. All the state parameters, all the inputs should be easily determinable by test or by simple measurements. We should be having a repeatable models. We shouldn't have much scatter in the modeling results compared to experimental data, and all the geometry and physics should be accurately incorporated. Now, if you use complex model, the disadvantage, of course, would be this, particularly if you have multi-scale, multi-physics models. But the disadvantage is often the computational cost, simulation time, and often we need detailed validation of such complex models with experiments. Otherwise, those models can be used, particularly in a design or a optimization perspective. So what we did, we moved on from this kind of complex model to a kind of one-dimensional network-based model with, if you can say, spring mass system, which we can call in FE what we call truss elements. So instead of 3D solid elements, we say if we can try spring mass element, which is truss elements, are we able to reproduce the physics of this kind of impact problems? So that's our main goal. So objective is simplified FE model, which is a 1D model. You cannot go beyond 1D. You cannot go zero-dimensional model. 1D model for Kevlar fabric. And first step is we will compare with a 3D detailed model to make sure our 1D model is accurate in terms of performance. So we take it forward, and we also compare with an experimental data, first point. So 1D yarns we are using to reduce the computational time, and we should be able to predict the fabric behavior, in such cases soft fabric, under low velocity impact, and we should be able to predict the damage and failure mechanisms without any loss of accuracy. So our main goal is we incorporate the right kind of physics, no compromise on that, and no compromise on the accuracy, but the simplified model. So we want to get very rapid results, because particularly for the response surface optimization, we should be able to run hundreds of simulations, even with the parallel computers, with different fabric architectures. So it should be a detailed parametric study. It is useful for studying effectiveness of various new fabric configurations that Australia's Defence Force is now currently designing. They will be using this model for that. So with that view, let's see the model implementation. So we have used 4 different types of projectiles, which are very standard, this kind of low velocity projectile impact, starting from a flat nose. Then we have a round nose, we have a conical nose, and then the 4th one is a conical frustum. This kind of covers, this projectile type has a significant effect on the damage mechanism when the projectile actually impacts, at the point of impacts a fabric. Particularly depends on the flatness, roundness, and the sharpness, and this is kind of in between both. So that impact, that affects the damage mechanism on the fabric, and as a result, the energy dissipation and absorption is significantly affected by the type of projectile. So we have covered these 4 common projectiles with the data given. We considered a velocity range of 30 to 130, which is considered in a low speed range in the ballistic range of impact. It could be a small projectile. We have determined the friction coefficient between such fibers experimentally, and we complied with literature data about 0.22, and we have used the projectile mass to be same, to be consistent at 7.5 gram, which is a small projectile. And the projectile was taken as a rigid body because compared to a fabric, its stiffness is quite large. So that is what our 1D model details. So we developed an unit cell which consists of fill yarns and warpians in two directions. And this is our kind of, you can treat as our unit cell or unit FEM element, which is one-dimensional in each direction. And we repeated that element to model the complete fabric, which was clamped at the end. And so this would be kind of our individual mesh. If you mesh this kind of unit cells with 1D element, which is equivalent to a truss element or a spring mass element, which doesn't even take into account bending, which normally happens in a hard impact phenomenon. So these are the dimensions. Our cross-section was 0.04564. Woven friction was 0.19. Unit cells, we had about 4,500 unit cells, which the results I'm showing here. And these are the properties for the warpian and filians. Young modulus, Poisson's ratio, ultimate strength, and thickness, what we have actually measured from the fabric we had. So we have used that typical values for this experiment. Now in reality, when we'll do optimization, the parameters like this thickness and some of the parameters of the fabric architecture will be variable, they will change. And some of them will have a statistical distribution as well, which have to be taken into account in the optimization. So what we need, the solver, the FE solver should be really fast, rapid, and accurate enough. So that's the part of the presentation I'm putting here in. So also we have considered the projectile impact at different angles and at different velocities, starting from 5, 30, 45, and 60 degree. And the fabric was fully clamped, 1 millimeter thickness at the four edges. So that's why it shows 101. So 100 millimeter is the effective area, effective side length, and 1 millimeter is the clamped area. And this direction, the warpian rounds, and the filian rounds in the perpendicular direction. So let's first look at this 1D model. Does it really work? So we can see this is a simulation of a flat nose projectile completely penetrating and piercing the fabric. And this is a round nose projectile completely penetrating and piercing the fabric. Now that videos looks nice, but what is important is here. Validation, we carried out two different types of projectiles. Earns were modeled with solid elements. In one case, A, and case B with our simplified 1D elements, which is truss elements. And we compared the response between supposedly more accurate 3D solid element model with a truss element based model, which is our simplified model. And so if we look at this slide, it's very important because that's what we did our validation study for our 1D elements with 3D elements. That's good, but we also had experimental data for this specific setup. So we compared our experimental results with both residual velocity with different impact speed. The residual velocity is the post-impact velocity of the projectile after it impacts the fabric. So what we found here, let's look at this diagram, what really happens when you have any impact velocity. So when you have an impact velocity is low, the projectile is rebounded. But that rebound doesn't happen with the same impact velocity. It is not a conservation law because for a fabric, inevitably there will be a damage. So if we simplify the case in physics, we are having an inelastic collision. So there will be energy dissipation. So as a result, you will see when the projectile rebounds, which means your residual velocity is negative, which is opposite to the direction of the initial velocity, the projectile rebounds. This line is not 45, it is less than 45, showing residual velocity is less than the initial velocity. Then we move on and we reach a stage where the projectile starts penetrating the fabric. So there will be a significant damage. So we can see the residual velocity actually increases significantly over a short linear distance. And then this point is where you have the projectile just penetrating, just comes out of the other sides, but it doesn't have any velocity. So which is what we call a limiting velocity and critical velocity, which we denote by V0. So note, we are not using V50 if you are familiar with the impact with the V50 limit. So we are using V0 limit, which is just the velocity we need to penetrate the fabric. So this is our V0 point where for a given impact velocity, in this case about 50 meters per second, the projectile just penetrates the fabric. So we compared these cases for two different cases, impact velocity versus versus residual velocity, both flat nose and round nose case. And we can see the limiting velocity is for 1D model and 3D model are very close for both flat case and round case. And it compares very well with this experimental data as well. So we are very satisfied that this 1D simplified model does reproduce the effective 3D model very accurately in terms of calculating the limiting velocity, or we call critical velocity. Not only that, it does match very well with experimental data. So we are very confident we can move forward with this model for our parametric study. Look at this thing. This is our key table, why we are motivation, if you want to call it. If you run 1D model for both flat nose or round nose, doesn't matter. If you run real 3D model, which we are very interested to do always, because of the very large degrees of freedom, it takes 33,200 seconds, so about 30,000 seconds to complete one run of the model, the full impact phenomenon. But if you look at what you may call Mickey Mouse model or spring mass or truss model, which exactly reproduce the response compared to 3D model and experiment, but takes fraction of a time to run it. So you can now see what is the benefit of going backwards using simplified models, particularly if you want to do a response surface optimization or parametric study. And that's the value. This table is the key why we have done this. So it takes a fraction of a time to run the model, even with any computers you can have. And it produced the response very well. Just to say, beyond this point, the projectile actually penetrates the fabric, so you can get the residual velocity is the same direction as the initial velocity, and this is the penetration response. So the last thing is we will present some parametric studies, what we looked at, and I'll keep it short, but I think I'm within time. So you can see we conducted this, as I explained, this dissipation energy versus impact velocity. If we see, we have compared for 4 different projectiles. And for each case, we can see a linear behavior when basically the projectile actually rebounds, and there is this degree of energy dissipation, or which is same as energy absorption due to the fabric damage, and as well as the friction between the different fibers. So there are 2 modes. Friction, there's a friction coefficient, so the fibers kind of rub against each other, so that's the energy mode of dissipation, and the fibers can fail if the ultimate strength is exceeded, like a spring mass system. You just break the fibers, each fiber, and that will cause an energy dissipation as well. And so then we hit a sudden increment in absorbed energy, which corresponds to significant failure or damage in the fabric. And then this part is fabric has been penetrated, so there is not much dissipation by damage anymore, but this energy, basically the kinetic energy dissipation by transferring to the eon. So the projectile transfers a part of its kinetic energy to the eons, which is then dissipated by friction and elastic deformation. And if you include plasticity in the fiber, it could be a plastic dissipation as well. So this is basically the formula we use to calculate energy absorbed. So difference in kinetic energy of the projectile, final minus initial. So in the last part is kinetic energy dissipation by transferring to the eon. So we have these 3 critical phases in terms of dissipation energy, and as we can see, the projectile type affects the energy dissipation significantly as we anticipated. So you can see if the projectile is flat, we can see the damage happens at a much later impact velocity, rather than if the projectile is sharp, like this conical frustum. If you take, we can see about 35, 37, we have the significant damage starting, whether with a flat or round projectile is 40, flat which is about 43, 44, 45. So this is the kind of range where the significant damage started. So this is mainly our concern if we are concerned about V limit or limiting velocity. So the projectile should not penetrate the fabric. So this is our main zone of interest, and we can see the sharpness or the geometry of the projectile affects the initial damage startup or initial damage and subsequently the penetration zone. So you can see if you have a very sharp projectile like a conical frustum, it quite quickly damages the whole projectile, and then the projectile penetrates completely. So what we really want from this side, we want to limit this sharp sudden increase towards the left. towards right, so that the significant damage is prevented with the increase in impact velocity. So this point should be as much as right as possible, as much as with high impact energy. Then what we looked at, a very simple thing to do, we normally don't use a simple fabric, we use a number of fabrics, but we can then orient the architecture, which we haven't looked at, but we just looked at if you include 1 fabric layer, 2 fabric, 3 fabric, and 4 fabric, and how it affects. The response is very expected. A 1-layer fabric, you can see the sudden damage or penetration starts at a very lower velocity. It is 44 meters per second, and then at this point, which is a kind of a limiting velocity of 46 meters per second, the projectile penetrates, and then it kind of penetrates through the fabric. If we increase the number of layers, our limiting velocity increases. The red one is 2 layers. You can see the linear response is extended for the higher impact speed. So up to this point, the projectile kind of rebounds, with of course causing damage to the fabric. So it is not a 45 degree, it is not equal velocity. So the residual velocity is always less, or rebound velocity is less. And then you can get the penetration, which is about 65 meters per second for a 2-layer. And then if you increase 3-layer, 4-layer, you can increase the limiting velocity, the velocity at which the projectile penetrates, from 65 to 92 and 114. So this can be nicely studied with a parametric study with a very simplified model, and the effect of layer, as we expect, is to increase the limiting velocity and provide more protection against impact. Simple diagram, 1 ply, 2 ply, 3 plies, 4 plies. You can see this is kind of a linear correlation between increase in the velocity limit and with the projectile number of plies. So which is very linear, and you can come up with a simple equation which can be used for the design or optimization purpose. And you can, rather than doing this analysis, we can feed this equation to the optimizer to calculate the sensitivity of the number of layers with the limiting velocity or critical velocity. Then we moved it to the impact angle, because a lot of times we neglect it, but impact angle has a significant effect on the penetration of the projectile. And as you can see, impact angle is nothing but projectile velocity has 2 components, Vy and Vz. Vy is transverse velocity, Vz in axial velocity. If your angle is the angle with the horizontal, which means if the impact angle increases, which means the transverse velocity Vy will increase and the axial velocity will decrease. So this is the effect of the angle on the velocity component, as we can clearly see. But what really happens when the impact happens, we have 3 different cases. If your initial velocity Vi, which is the magnitude, is low enough, which is less than the critical velocity, then what will happen, basically, after the impact, this transverse velocity will reduce and the axial velocity will be reversed, which is like a rebound, but the projectile will be slowed down in the transverse direction. And this is what you can see in this residual velocity plot. When your velocity is 30 meters per second, you can see the Y velocity is reduced, but you can see the Z velocity is actually reversed, so it is negative, and it never penetrates the fabric. So we are in the safe zone. But this negative velocity is actually linearly increasing with impact angle, simply because if you increase the impact angle, you increase Vz. And as a result, your residual velocity or rebound velocity increases. So it's very simple to understand. Then we have a limiting case where Vi is equal to Vc, so the projectile just penetrates. Against the Vy is significantly reduced and Vz is just brought to 0. And then if you increase your velocity, so the projectile actually penetrates, your behavior of Y velocity is positive, as you can see, which means with impact angle, you increase your Vy, so you increase your residual velocity or rebound velocity, and that increases with the angle. For both cases of Vi 60 meter per second and Vi 90 meter per second, we can see with increase in impact angle, we have an increase in the transverse velocity or penetration velocity. On the other hand, with an increase in impact angle, we can see the axial velocity after penetration actually decreases with impact angle. So you can see that is what schematically shown in this picture with an impact angle increase, because if you're increasing impact angle, you are increasing initial Vz component, and as a result, you are actually decreasing the residual Vz component as well, or the post-impact Vz. So that is what is reflected in the graph, and you can develop such nice diagrams by very simply running these models 100 or 1,000 times very quickly. Each model run with a very slow computer, it took
480 seconds. So you can easily run many models in a day and create your whole response surface of impact speed, impact angle, number of layers, and any other complicated parameters, fabric properties, friction. You can add as many design variables as you like and create your optimum response surface. So that was the goal of doing such analysis. So this was a pretty preliminary part I thought of presenting here. So in conclusion, I would like to emphasize that our objective was to develop a sufficiently accurate, we don't want to compromise on the accuracy, then optimization will be meaningless, a simplified FE model with the most basic elements we teach in the FE lecture in the first day, truss element, to model the impact, which is a very complex response, because impact normally involves large deformation, nonlinear response, contact, damage, fragmentation. So this is what impact is about. So all of this has been captured in this very simplified truss element-based model, which can fail. 98% compute time reduction compared to 30,000 seconds to 500 seconds. That's the key goal. I think I should highlight this, why we did it. For the simplified model, it slightly underestimates the value of the critical velocity, but error is within 2.5%, which is a very good in terms of engineering accuracy. We have seen some physical characteristics of the effect of projectile geometry. For example, sharper projectiles generate more deformation and damage on the fabric and consequently lead to higher energy absorption. If we increase the frontal area of the projectile, like a flat projectile or cone frustum type projectile, it causes a small variation in energy absorption. So more layers, if you use layer count, will always increase your critical velocity, provide you more protection against impact. So we have studied 1, 2, 3, and 4 layers, and we have clearly seen the effect of number of layers. Increase in impact angle, increase the velocity limit and the dissipation energy. So impact angle is very important, which impact angle we are designing our system at. And we shouldn't include the effect of the transverse velocity if the projectile is impacting at a certain angle. So we kind of, in summary, covered the basic physics and geometry requirements and the accuracy requirements through this simplified model for the basic purpose of a response surface optimization, which we are working with Australian Defence Force in their soft body armor design group. This, of course, model doesn't capture a lot of other complex things. If we need to do, I need to go back to my previous work, which was multi-scale complex damage model, which I presented at a conference 2 weeks before in Italy. With that, I would like to conclude. So further impact, we are trying to use a cohesive matrix between layers. High velocity impacts we are moving into. Also, we are looking at blunt object, like a knife and other blunt object impacts, and moving into the body armor standards to incorporate in these models. But we need to go more complex. We should see how we can keep the model simplified with 1D elements, but still incorporate complex weaving or fabric architecture and even interlocks between the fabrics. So that would be our next step. Keep the solution time simple, but increase the complexity in the physics and the geometry of the problem. So this is the motivation, this is the direction we'll be moving. With that, I would like to thank you very much for your patience and for being here. As a chair now, I will open the paper for questions.
Okay, can you go back to slide 15, please?
15, yeah. Yeah.
No.
16 then?
No, one before that.
Yeah.
14, okay. How sensitive were your results to your mesh?
Not sensitive at all. We have done mesh convergence study. Once you have reached this number of elements, which we presented 14,000, it's 14,000 or 4,000, for this case, 4,000 elements, we did a convergence study. Our mesh convergence resulted within 0.2% difference. So we attend the mesh convergence. Important is we need at least one element between these two lines. At least two elements, sorry, not one. If you have more than that, your results become like you're replacing one string with another 3 strings, which is one element doesn't matter anymore because the string is the same. Unless you are bending, then only it will matter.
In our experience with finite element analyses like perforation problems, our results are extremely mesh dependent.
If you use 3D mesh and if you use continuum fracture.
I mean, we looked at 3-dimensional problems. We didn't have one It's quite mesh efficient.
I think we can get away with the mesh dependency because we are not modeling a fabric matrix damage, delamination, interface damage, which is normally we do for a composite, where there is a continuum matrix and the fabric interaction play a role. This is just a fabric, and we can model as a 1D element, and that's the reason we kind of overcome the mesh resolution dependency with the damage modes in this specific case. But I'm sure when we write the matrix, we won't be able to do it as easily.
Thank you.
What kind of failure criterion did you use? I guess I understand.
What we did, we computed the ultimate strength of the fiber. And we said a fiber fails if it is longitudinal stress, which is the stress in the truss element, exceeds the ultimate strength. And the ultimate strength was computed, I put in a table. Yeah, that's the story.
Okay.
Very simple.
And it seems to work. So why do you need to use cohesive elements in the future?
If you use matrix. If you use matrix and if you have this warp and field fibers are kind of joined together with the matrix. So you have an interfiber strength. Now we have a friction. So fibers can slide and we have a friction dissipation. Okay? Although we can incorporate the friction force also, which is incorporated on the fiber, which adds another one-dimensional force like a shear force on the top and bottom of the fiber itself. And if you have matrix, you have to have a cohesive dynamic. You have to implement a criteria how the fiber matrix interface fits. And that's why the cohesive elements will come.
For the fiber matrix interface,
Interface, yeah.
not the delamination.
And lamination.
And, but the,
With this we don't need. Only fabric we won't need. No.
I mean, these look successful, so you don't.
We don't need
show
this
that
for
you
fabric,
need
no.
cohesive elements. That. Thank you.
I think you have to ask, I'll go next.
Yes. Regarding the properties you use, those are just only fiber properties, or?
These are only fiber properties. Yeah.
Alright.
Yeah, properties. Yeah.
The general.
And then for the year.
And
So
then,
my element is actually here, not I was using fiber. It's actually here, sorry.
all right, and then it will be not isotropic, isn't it? So you consider it isotropic for your model?
Here is isotropic along the axis. And because, as I said, we ignore the bending, we are thinking as if we replace the fabric with a sketch of rubber bands. So it's like a bunch of rubber bands that are replacing the fabric. So we consider the transverse property doesn't matter because bending is not included. So only the axial property will matter. If we include bending, yes, then transverse property of the ear and E value will be different than longitudinal property. So we have to use EX and EY for the ear in that case. We have just even truss element.
And just a final question, what about the waving? Because if you have the yarns are waving on a...
We can model that because our unit cell looks like this. So you can have a wavy, like a truss.
All right.
You have a wave, you model as a 3D truss. And you can use many elements, truss elements to model that waviness. So we want to try how it works. You know? That's what they wanted. They didn't want a complicated model. They want the engineers to be able to run it quickly for many cases. And they have the experimental facilities so they can calibrate with this. I think I'll go to the end and then if you have a question, I come back.
About the validation, have you also compared the size of the holes in Keva or just the residual velocity of the hole?
We compared the residual velocity and we did compare the size of the hole as well. But I would like to tell you when it penetrates, the size of the hole is very close to the projectile diameter.
Yeah, but for the conical projectile it goes
No, this is,
after
we did compare the diameter zone. How many, what we really compared, I'll tell you, we compared how the area around the point of impact and how the holes created by the failure of the fibers. So we compared them that closely matches. Because we are just here in the fiber, here, so not the fiber, here in this case, nothing else happened.
Yeah, so it's related with the question again. If you have waves, you're going to have contact between the trusses, no? How do you model that?
We friction. So what we did, because we have two trusses, we know the coordinate of this point, we know the coordinate of this point, and we know the initial configuration.
Okay.
So from that, we assume we can detect the contact between the two rods in space. So you know geometry, right? And at the contact point, we know the friction,
Okay.
right? Then we estimate, because
Friction means we need to have a frictional dissipation, which means we need a normal force. Although we are not modeling bending, we have to have a normal force between them. But fortunately, these trusses are free. So from the reaction at the nodes of the trusses, you can get a simple free body diagram to get the contact force, which is again based on 1D truss approximation. Once you know the contact force, that is our normal force. And that normal force times friction gives you a force on that both the trusses equal and opposite Newton's third law, and which kind of added to the truss element at the source. So that's what we did. So it's a very simple model. That's what I said. We kind of went backwards after a long time with this. But I found it's very effective and it works, and our client is happy, the defense is happy to use this model. Any further question? I think a lot of questions for the chair, which is good. It's your time. Any other question? If not, if you have any question, you can ask me later. What I would like to do, I would finish off with a quick thing, which I think I should do. I forgot about it, which is more important than this talk. It's I must thank all my students, collaborators, and the joint funding body, which is Ministry of Business, Innovation and Employment. And then there's an invitation for you to Australia. If you want this lifetime opportunity. Now when I say people go to Australia, it's too far. Then I ask two questions. What about if I give you an offer to go to Moon or Mars? Will you say it's too far? You will not say. And what about your forefathers? The European great powers who traveled months and months across Atlantic and out the Pacific to reach even to Australia. Now you can reach in 20 hours. And that time it was 20 months. So that gives you a thing. And this is not any other A conference. This is a very prestigious conference, international conference on mechanical gearing of materials. And many of you are familiar with this conference. Last two were held in Italy and Germany. It's every 4 years only. Started in '71 in Japan and never happened in Australia. So this committee had actually contacted me and pushed me to organize this. It never happened in Australia. I think we feel bad about it. Why would we organize? I said, look, if your Europeans are going to come, they are happy to organize. So we are organizing a conference in Melbourne, which is a wonderful city. Last 5 years, it has been voted as a top city for living, the best livable city if you Google it. So you'll have a great time, and I would like to cordially invite you all to come. The abstract submission is open till end of November, so I would like to consider this and come to Melbourne. So this is my team of students, my group at Melbourne, Australia. And this is, you can see the complex fractures create extraordinary beauty. This is 12 apostles, which is about 2 hours from Melbourne. So you can see this kind of exciting rock formation and cracking in the rock. So if you want to do some fracture research on geomechanics or rock mechanics, this will give you a great time as well. So with that, I would like to conclude my presentation and subsequently conclude my session. Thank you very much for your patience and that you attended the session.